Right, hello everyone. Welcome back to another Chemistry Squad. My name is Nketia, or just NK for short, and we're back at 6 o'clock on a Thursday for another My Tutor Chemistry Squad. Super excited to be here, um, and just excited just to get on with some chemistry. Just a few ground rules as per normal. As a few of you are sort of rolling in. Mohammed, hi, good to see you. Thanks for joining again. Um, as always, these study squads are for you, and the only way we at My Tutor will know whether you find them useful or not and what you want them to be is if you let us know. There is a feedback form in the description. There's a link in the description of this video which you can click on to sort of give any feedback that you can think of. So, by all means, the more feedback you give, the more we at My Tutor know how to make these sessions useful for you. Additionally, it's super important that if you like the video, you just give that good old like button a smash. And if you have any school colleagues who might find these series or these live streams useful, there is also a link that you can share with them and they can sign up as well, all for free. Again, these sessions are tailored to help all of you in your academic endeavors. And so it's super important that any feedback you give us, then we know how to tailor them to make them useful for you. Um, but in the interest of time, we won't spend too long getting comfortable. I think we'll just sort of jump right into it. Today, I wanted to go over enthalpy, so going over endothermic and exothermic reactions. This is actually our fifth lesson of the squad series. I think it's our fifth, it might be our sixth. So we're at that halfway point. And as always, I'll always ask you guys at the end of the session what you'd like to cover next, or what you'd like me to cover next. Um, if I don't necessarily get a response, I'll probably go over rates of reaction because I think that always goes in quite nicely with enthalpy, since we're always sort of thinking about energy with that train of thought. But yeah, generally, that's what I would say. I do have a quick question here from Mohammed, though, which I will answer. I know we have a Q&A towards the end, um, but um, I'll answer it now. So Mohammed asks, what's a better tutoring website, the profs or my tutor? Um, because the profs have teachers from Cambridge, but it's more expensive. Um, good question. I can't comment on that. Purely because I don't necessarily know what the profs is like. All I can really say is that I think my tutor's a fantastic platform. All of the teachers are vetted and interviewed from Russell Group universities, and only a select few um, tutors are selected. So by all means, I can't really comment on the profs, but I think my tutor is a brilliant platform. Wasn't this lesson about electrolysis? You know what? I think you might be right, Mohammed. I think it is about electrolysis. Um, in which case, we can certainly go over electrolysis. Not a problem at all. I will change the title of this to electrolysis. Thank you for reminding me. As you can tell, it's been an incredibly long day and I don't have my notes, so I've not been the most organized. Electrolysis, there we go. That's updated. Okay, so let's talk about electrolysis then in today's lesson. Last week, I know we spent a little bit of time thinking about reduction and oxidation. So thinking a little bit about electron transfer. I can see a few more people rolling in, so hi, don't be afraid to say hello. But on that note, Mohammed, if you want to answer, by all means, just go for it. I want you to remind me, how would we define oxidation and how would we define reduction? Again, we're just going to focus about both of these terms in the context of electron transfer. I know we can talk about oxidation and reduction in terms of oxygen and in terms of hydrogen as well, but I just want to focus on electron transfer since that is what we would consider the more conventional way of looking at oxidation and reduction, at least when we're talking about electrolysis. Okay, and it is relevant because when we think about electrolysis and what actually happens, um, we see either oxidation or reduction at either of the electrodes. Fantastic. So you smashed it, Mohammed. Well done. So Mohammed has said that oxidation is the loss of electrons and reduction is the gain of electrons. Spot on. And a really good way of remembering that is thinking of the mnemonic oil rig, where oxidation is loss and reduction is gain. Now, if we think a little bit then about oxidation and reduction in the context of electrolysis, I think the next thing to sort of think about is, well, why do we bother with electrolysis in the first place? So hopefully, if you haven't already, you'll know about something called the reactivity series. And the reactivity series is a list of different metals, okay, all with varying reactivities. Um, and in that respect, your different metals have different levels of stability. So, Mohammed, do you have any ideas of not question, sorry, metals that might be lower down the reactivity series and any metals that might be higher up in the reactivity series? Just one example of each metal, or anyone for that matter. I only say Mohammed because he's the viewer who is answering the most at the moment. But if anyone else has any other suggestions of metals that might be higher or lower, then by all means, do share. What do we think? Which metals are lower down the reactivity series? Which metals are higher up in the reactivity series? All right, spot on. That's a really good answer. Gold is the lowest and potassium is the highest. I'd agree with that. Now, the reactivity series, as the name suggests, is a good way of seeing what's the most reactive and what's the least reactive. And that's quite important for us because a lot of those metals are quite useful to us on a day-to-day basis. When we think about things like gold and comparing them to things like potassium, that then helps us explain how we actually find them in nature. So, for instance, you might find gold, for instance, in a relatively pure form. And I don't mean just blocks of gold in nature, but I mean you probably won't find things like gold oxide or platinum oxide, for instance, because they are quite stable in themselves. They're quite unreactive, so they have no natural tendency to form some type of compound to achieve stability. On the other hand, things like iron, you don't tend to find pure iron on its own. You tend to find things like iron oxide. The ore is called hematite, for instance. Okay, and that's generally because iron is a lot more reactive, so you tend to find it in an oxide form. Now, that's quite important for us to understand because we need pure metals a lot of the time. Sometimes that's because we want to use the pure metal in its own right, and in other instances, it's because we want to take that metal and we want to then transform it into something else. Okay. So for instance, iron, for instance, we can use iron as a component in steel, which we know is an alloy that consists of both iron and carbon as a bit of a base, but we can add other things in there. So stainless steel, for instance, is a good example of an alloy which contains iron, steel, and chromium and other sort of substances to give it that stainless lack of reactivity property that we know stainless steel for. When we think about the reactivity series, I guess it's also important to remember that when we then think about obtaining metals, where you have the reactivity series will then determine what method we use to obtain the metal. Now, what I'm going to do is I'm going to ask all of you, well, some of you might be on your phone instead of laptops, so this might not necessarily be the easiest way of doing this, but I'm going to try and get a picture of the, oh, perfect, I've got a picture. Okay, you can see my screen. Fantastic. The reactivity series. Let's see. So here's a good example of a list of the reactivity series. Let's see. Anytime I open a new window, my laptop does lag a little bit. It is an older laptop, so I mean, I say that it's a MacBook, um, but by all means, it's a there we go. Here's an example. Oh, here we go. So you should be able to see that hopefully. I'm just trying to drag it. I don't think it's moving. No, it's not moving. Fine. Okay. So if we look at our reactivity series, for instance, things like potassium, sodium, and calcium at the top, things like copper, silver and gold are right at the bottom, copy and paste it. So copying and pasting it doesn't necessarily work with Streamlabs, um, because I'm not. It's a case of what do I copy paste it to. Um, let's open it in a new tab. Let's try that. Is that done? Oh, there we go. Smashed it. Okay, cool. So that's what we've got there. Okay, so this is your reactivity series. Um, so you can see here that things like potassium and sodium and calcium at the top, things like copper, silver and gold are at the bottom. Now, one thing you can do is you can almost group them and think anything higher than the next metal in the reactivity series can displace something that's lower down. So tin, for instance, can displace lead from lead oxide, for instance. Copper can displace silver from silver oxide if you had it, for instance. Okay. Potassium can displace sodium. Okay, and so on. So hopefully that's made a bit of sense so far. Now, in terms of the different ways in which you'd extract a metal, okay, we have different methods. Because the session's on electrolysis, I will go on to sort of thinking a little bit about electrolysis, but I do want to sort of touch on the other methods really briefly. So one way in which we can extract a metal is using a blast furnace, and then we generally use this for things like iron, for instance. Okay, so you might use a blast furnace to extract iron from iron oxide, for instance, and we can use carbon for that because carbon is higher than iron in your reactivity series. Okay, um, so that would be one method. Other methods could just be using other metals to displace less reactive metals. Now, you can't always do that though, because when you reach things like potassium and sodium, that becomes a bit of a problem because then you have nothing above potassium. So this is where we then use electrolysis, and I'm actually going to get a diagram of electrolysis up in the lesson space for you. Mohammed has asked, what about bioleaching? Well, bioleaching doesn't necessarily involve using multiple methods. So with bioleaching in particular, the idea is that let's say you took a let's say you had like copper oxide, for instance, okay, and you could essentially you obtain a leachate, okay, from let's say a bacteria or some type of microorganism. Okay, and the idea is you can then obtain I say I'm using copper as an example, the copper ions from the leachate from the solution. Okay, um, so both bioleaching and using plants, for instance, in order to obtain the metal are both viable methods. Generally, these would be reserved for the less reactive metals, so I'm not saying there's a particular ceiling, but I generally see things like bioleaching used for things like tin, lead, copper. So maybe anything below tin. Okay. So that would be bioleaching. Okay. Um, does that make sense? Do you have any other questions about bioleaching? Hopefully that does make sense. If not, then that's not a problem at all. So again, remember bioleaching, the idea is that you're using bacteria, okay, and the idea of using your bacteria is that you produce a solution, so a leachate, okay, and you can then obtain the calcium ions from that. So Mohammed has asked, how do bacteria actually eat the metal itself? Um, I don't necessarily think it's a case of the bacteria. I don't know about eating is probably the best way of thinking about it. Um, I suppose the idea is you're using bacteria to extract the metal. Okay, so let's say, for instance, you have I don't want to use E. coli as an example because that can be quite pathogenic, but let's say you have a bacteria that has the physiological characteristics to break down an ore. So maybe they use enzymes, for instance. Okay. At GCSE, you're not necessarily required to know the ins and outs of it in great detail, but let's just say they have an enzyme or they produce some sort of physiological substance that is able to maybe reduce the oxide, for instance, and just obtain the pure metal. Okay. So some strains of bacteria, they sort of break down the ore to form an acidic solution that then contains the pure iron in question, which is what we call that leachate. Okay, we can then take the leachate and the ions in it and then reduce the ions to the solid. So if I had copper 2 ions, for instance, I reduce them to then form copper metal, since we know that if we reduce cations, which are positively charged, we then form atoms because we're adding electrons. Okay, so that would be bioleaching. Okay, phytomining, which is the alternative, so using plants, okay, that as plants grow into the ground, all these roots are going to take in all these different ions that we found in the ground or maybe found in the ore. We then burn the plant and we then obtain the ions from the residue, okay, and then we then have that metal. So again, you could use copper as an example. Okay, hopefully that answers your question. Give me a quick thumbs up in the chat if it does. If not, not a problem at all. Ask another question and then we'll go through it. It does. Fantastic. Great to hear. So let's continue. If we then, let's get a quick diagram up of electrolysis. Uh, electrolysis. So I think this is a good diagram when it decides to load. Whenever it decides to load. Technology for you. Okay, maybe that's not the best, but that's fine. We can use this one. Open image in a new tab. It's a very tiny image, so maybe not that one. Let's try a different one. That looks slightly more promising. Fantastic. Okay, cool. So, electrolysis as a term, okay, we can use it to essentially demonstrate what the what the process is. If we break down the word electrolysis into two separate words, you have electro, i.e. electricity, and lysis, meaning to split. So we are using electricity to split things up. Okay, that's essentially what we're doing here. So if you took a compound, let's say sodium chloride, for instance, okay, and I'm going to explain two different scenarios because at GCSE you need to be able to explain two different cases. Electrolysis of binary compounds where it might be molten and you just have the two ions, or if you have an ionic compound dissolved in solution, that's slightly different because then you have water thrown into the mix as well. So if you have, let's say, sodium chloride, okay, it's molten. So remember that in a molten ionic compound, okay, the ions are free to move around because they are no longer held together by strong electrostatic forces of attraction. The idea is that the ions go to separate electrodes. The positive ions, which we call cations in chemistry, will go to the cathode. Anions, which are negatively charged, will go to the anode. Now, if anions are negatively charged and they are attracted to the anode, then it makes sense that the anode is positively charged. Similarly, if cations, which are positively charged, are attracted to the cathode, then it makes sense that the cathode is negatively charged. Okay, so we've sort of understood it from that perspective. Okay, so cations go to the cathode, anions go to the anode, so we've understood that. The other thing to then think a little bit about is what actually happens at either of these electrodes. Now, generally, if cations go towards the cathode and the cathode is negatively charged, we would expect reduction to happen at the cathode. And that's exactly what happens because we see the cations, which tend to be metals, they will gain electrons, and in gaining electrons, they then become the normal metal. They just become atoms. Similarly, at the anode, we would expect to see oxidation because anions are negatively charged. They would lose those electrons, and then we then end up with the normal non-metal. Okay, so that would be what would happen if you had a molten ionic compound. So again, if I just had the sodium ions and the chloride ions, okay, in a molten, I don't want to use the word solution, but in its molten state, my sodium ions will go towards the cathode, and my chloride ions will go to the anode. So I form chlorine at the anode, and I'd form solid sodium at the cathode. So that makes sense. The difficulty lies in when you have a solution of an ionic compound. And the reason it becomes slightly more challenging is because now you have water, which can also become electrolyzed and form different ions. Now, does anyone have any ideas as to what you would form at each electrode? What do we think? I want to see some ideas in the chat. What do we think? So remember that at the cathode, okay, your cations are positively charged, so they're going to go to the cathode. So there you're going to see reduction at the cathode, and you're going to see oxidation at the anode. Okay, so let's think here. What do you think would happen if I had an aqueous, I had solution of my ionic compounds? I'll give you one more minute to think about it. Would I still just form the same ions all the time? Would I form hydrogen ions or hydrogen at the cathode and maybe oxygen at the anode all the time? Or is it a bit of a mix? What do we think? Okay, Mohammed, you said hydrogen ion for the cathode and the anode for the oxygen. Right. In short, you're not wrong at all. It comes down to a half and half situation. It really depends on what you've actually got, as is the case with chemistry. So, there's a general rule that you can use for both electrodes that you can remember for your exam, and it makes things a lot easier to work with. If you have at the cathode, we're going to focus on the cations first. If your metal is higher in the reactivity series than hydrogen is what you'll form at the cathode. If your metal is less reactive than hydrogen in your reactivity series, then you form the metal at the cathode. So I'll say that again. If you have a solution of your ionic compound, if the metal is more reactive than hydrogen, you form hydrogen at the cathode. But if the metal is less reactive than hydrogen, you form the metal. So generally, the more reactive substance will stay as the ion, and the less reactive substance will go to the cathode. Now, that one can be a little bit challenging to remember, but if you can get your head around that one, you can easily get your head around the ones for the anions, for the non-metals. Generally, for the non-metals, you'll always form oxygen unless you have a halide, so one of your group sevens. So either fluorine, chlorine, bromine, or iodine. If you have one of those, that is what you'll form at the anode. Otherwise, you will always form oxygen in aqueous solution. Okay, and that's electrolysis. Now, generally, the idea behind electrolysis is that it's very expensive, it requires a lot of energy, but we're restricted with regards to how we can actually extract some of these more reactive metals that we use on a day-to-day basis. Sodium is incredibly important. Um, Potassium is incredibly important. Okay. And calcium is certainly important. So from that perspective, having a method like electrolysis is incredibly important. Even aluminium, which we use for so many things on a regular basis, also incredibly important. And we use electrolysis to obtain pure aluminium from aluminium oxide, which is how we tend to find it in practice. Okay. And that is electrolysis in a nutshell. I think this topic is really interesting from a learning perspective because there are so many different areas of the GCC course that there's a bit of overlap. There's a bit of overlap with ionic compounds, for instance. So it's important that you understand structure and bonding from an ionic perspective. And there's also overlap with oxidation and reduction. So it's also super important that you have an understanding of what oxidation and what reduction are, know how to write your half equation, so and how to balance them accordingly, how to show oxidation on one half equation, how to show reduction for the other half equation. Okay, so that's super, super important. Okay, but otherwise, that more or less sums up electrolysis. Now I'm just going to move over to um, the Q&A session. So we're still here for 15 minutes or so. So if anyone has any questions at all about chemistry, about revision, about GCSEs, we're here for 15 more minutes or so. And we can also set out what we are planning on doing next Thursday. I think we could go over enthalpy. But if anyone has any other burning desire to go over anything else, no pun intended, then by all means, do pop something in the chat. Um, because any suggestions are good suggestions. So do say. So Mohammed, you've asked, can we do GCSE exam papers? We certainly can do. Um, chemistry paper one. So did you want to go through like the chemistry paper? Like just go through each page? We can certainly do that. We can certainly do that. If people will find that useful, for sure, we can do that. My question is, will we do that for the rest of the sessions? So I think we've got 5 sessions left. So I don't know. You've got mocks in November. Okay, well, if people have mocks in November, then by all means, and if people will find it useful, we can certainly do that. That's fine. Yeah, that's fine. We can certainly do that. I think the session next week, it may just be 3 more, actually. I think these go on to the 30th of July. I need to double check. But generally, yeah, we can certainly go over past papers. That's fine. Now, does anyone else have any questions at all? Do you decide how many sessions you do, or is it the My Tutor company? It's my tutor. So my tutor decide how many sessions are done for each series. It's actually 8 this time, so I'm well over halfway actually. So we've got 3 more sessions. So, oh, actually no, 2 more sessions. I stand corrected. 2 more sessions. So we only have 7. So we've got one next week and then one the following week. That's right. That's right. So we've got 2 more sessions actually. So my tutor decides how many we do. So if you want to do more, are you able to? So essentially, my tutor, to the my tutor team, will say how many squads we do, like how many squads we'll do a term. And then we'll do different ones. So there's a maths one running at the moment. I think there's an AI or a coding one happening at the moment as well. And then there's a science one. Um, and then we'll do a squad series every term. And then, different tutors will run different squads. And we'll just be told we have this many sessions to do. And then we are given we're given the creativity to structure them how we'd like. But I think the key thing that um, that my tutor that we at my tutor ensure is that the content that we cover is appropriate to you guys, and it's content that you would find useful, which is definitely why we encourage feedback from all of you. It's why we try and encourage as much engagement as possible, because then we know what does work and we know what can be improved on and what you find useful. Um, so, yeah, the more feedback, and there's a form, the link in the description of this video. There is a link. If you click on that, you can type as much feedback as you want. The more feedback, the better. Because then what we can then do is go away. We can also then look at all of that information, all of that feedback, and then we can use that to then put together more resources that all of you as students find beneficial. Um, Hope that answers your question, Mohammed. But very good question all the same. Does anyone have any exciting plans this evening? Now, the summer holidays are coming up, so does anyone have any exciting plans for the summer? Is anyone going away on holiday at all? So, Mohammed has another question. Do the viewers decide which session they find useful, and do they decide which session to do based on that feedback? So, I think this is, again, that's a really good question. I so that's more behind the scenes stuff, which I'm not always necessarily involved in. However, um, if students say that there's a demand for a certain type of subject, it could then be that if there's a tutor that can then lead that squad, they'll then approach a tutor or sorts of or ask different tutors to run those squads, for instance. Um, Sometimes, if it's the content within each squad, it could be that like let's say in my case, for instance, with chemistry, um, sometimes what we'll do is plan everything in advance, but it could very well be that if I had planned a session on, let's say, rates of reaction, and actually, it's quite clear in the session that you would find calculations more useful, then I'll then tailor the next session to then be on calculations. So that's more tutor-led in that respect, which is the great thing about my tutor. Um, we don't have to be very strict with regards to what we cover. Again, the aim is to ensure that you find it useful. So we're always happy to sort of tailor the plan a little bit and be a little bit flexible just to ensure that you guys get the support you need as you transition from, before GCSE to GCSE to A level and then after that. So that's what I would say. I mean, every tutor who runs their squads works a little bit differently. So I can only really comment on myself. What do I think the most difficult chemistry topic is in GCSE? Another really good question. I think it depends on who you are, to be honest. It's interesting because I was interviewed today by my old university. They invited me back as a speaker, and they asked one question that I had from someone in the audience was, "What's one thing about my job that I find the most challenging?" And I said, "I think what you find challenging depends on who you are as a person." Now, for me, if I had to go back to when I was a GCSE student, I think I found the calculations more difficult. And that's not necessarily because I didn't think I was good at maths. It was more because I wasn't a huge fan of maths, purely because it was just numbers and I didn't get the relevance of it at the time. Um, However, now, if I look at after doing GCSE and A level chemistry and then modules of chemistry at university, I would say that organic chemistry is actually quite challenging because there's a lot of depth to it. Um, so I think at GCSE, I think maybe organic chemistry. I think overall, I think organic chemistry is probably the most challenging, because it's so different to what you've gone over before. It's the first time you've drawn molecules and you learn about reactions. So there's a lot of stuff there. sort of cram into one space. So understandable. I think organic chemistry is the most challenging. Good question though. Which university did you go to? I went to Durham University. Um, it was really fun. I really enjoyed it. It was a brilliant course. The structure of the course was really really good. So yes, I went to Durham. So yeah, no, it was good. Can I do the Harbour process later after going over a chemistry paper? Yeah, we certainly can do the Harbour process. So that's a little bit of equilibrium actually. So yeah, we can certainly do that. So I think next week we'll go over a chemistry paper, and the week after we'll then go over the Harbour process, and then I think that's it. Um, then that's this chemistry series for this term. Um, I'm sure we'll do another round of chemistry squads next academic year, so maybe in September, October. There's one more. I'm not too sure there is one more because I think the dates end on the 24th of July, which means that next week is the 13th. Is it? Yes. That would be 7 sessions. I think I have 7 sessions rather than eight because I started a week later. I'm not 100% sure on that one though. I would need to double check with the My Tutor team. But I think we've only got 7 sessions. So I think we've got a chemistry paper and then the Harbour process. But generally, that's fine because I'm sure my teacher will do more of these chemistry squads next academic year as well. But that is dependent on whether there's demand for them. So if you do like these, then do make sure to stress that in your feedback because then it means that we can run another squad. Um, and who knows, maybe I'll be asked to run the next squad. Will we see you again? That's a very good question. Depends. Depends on whether we run the squads again. Potentially, it might be me, it might be another tutor. But like I mentioned before, or earlier on in the session, every single tutor on the My Tutor platform, we're interviewed. You know, intensely is not the right word. We're interviewed very, very precisely with really specific criteria. Um, so if not me, I'm sure the next tutor will do a brilliant job of running the chemistry squads. If we have chemistry squads next year, but who knows? Maybe this will take on a completely different form. We're always trying new things at my tutor to support all of you in your academic endeavors. So watch this space is the short answer, is what I would say. Yeah, watch this space. I am going to get some wipes for my glasses because I won't lie to you, my glasses are not the tidiest at the moment. Good thing I'm short-sighted because at the very least I can still make out what the screen says. Am I in a lab? No, I'm not. I'm at work. So I work as a hospital pharmacist. So I'm actually in a clinical office at the moment. So what you can see behind me is a hang on. There we go. Much better. So what you can see behind me is a an air conditioning unit and some shelves. I'm not in a lab. No, I'm in a hospital. Obviously, as a member of staff, not a patient. But yes, not in a lab. Although I think it'd be quite cool if I had like a lab as a backdrop, might add to the whole ambiance of being a chemistry tutor. I think that's quite cool actually. Okay, so I think we're going to sort of. Are you able to treat yourself if you're a doctor? Um, I'm not. Well, I'm not a doctor. I'm a hospital pharmacist. Just unless this is a question, a rhetorical question. If you're a doctor, are you able to treat yourself? I'd argue not quite. I don't necessarily think that's best practice. It's not necessarily encouraged as best practice. In the same way that as a pharmacist, um, I might know how to treat myself, but I would still go to another clinician for a second opinion. Um, so even though I might say these symptoms, it's likely this, I should be treated with this, I would still go and see another clinician just for a second opinion, which is important in healthcare because you always want to get a second check. Um, because if you don't, that's how mistakes happen, is what I would say. That would be how I would answer that question, I think. Okay, so I think we will leave it there for today. Thank you for joining, everyone. Again, there are no squads without you. If you did like this session on electrolysis, make sure to smash that like button. Next week, we will go over a chemistry paper one, past paper for GCSE, and we'll go over the answers as well. So what we'll probably do is go over each question one at a time. I'll get you all to sort of answer the question there and then I'll give you feedback and tell you what the answer is and sort of explain the question and then how you'd answer it. So it'll be a really, really fun session. But otherwise, I hope all of you have a lovely evening. Stay safe, and I will see you all next week for another exciting chemistry lesson. But take care until then.